Good evening, good evening. On behalf of the Encounter, welcome everybody here present and those online. I'm Massimo Robberto from Space Telescope Science Institute, and I will facilitate this meeting on weather, on global warming, on one of the topics that are more important, I think, present days, one of the most debated with of great interest scientifically, but also culturally, with all the implications on politics, economics, that I think we are all aware of. We want to take a fresh, honest, loyal look at what's going on. Before the opinions, we want to know the facts, and I would say the methods of how we understand what is happening. And for this, we are facilitated today by the presence of two top scientists, top weather scientists that are spending their life studying this phenomenon. So I will introduce them briefly. On my left, Dr. Kerry Emanuel is Cecile and Ida Green Emeritus Professor of Atmospheric Science at the Massachusetts Institute of Technology, where he was on faculty for more than 40 years, 81 to 2022. His specialty is hurricane physics, and he was the first to investigate how long-term climate change might affect hurricane activity, an issue that continues to occupy him today. Emanuel is the author of, or co-author of, over 300 peer-reviewed scientific papers and 3 books. He was a co-founder and co-director of MIT Lawrence Center, a climate think tank devoted to basic, curiosity-driven climate research. Dr. David Romps is professor of climate physics in the Department of Earth and Planetary Science at Berkeley, and the faculty science in the Climate and Ecosystem Science Division of Lawrence Berkeley National Laboratory. Professor Romps studies the fundamental physics of climate and educates students and the public about global warming. He received a bachelor in math and a master in physics from Yale and a PhD from Harvard. He currently teaches the popular course Introduction to Climate Change at Berkeley. The questions that we have are basically those already in the title, so it's easy for me to start with the first question. What do we know and what we do not know? Kerry, give us a little introduction about what is global warming. Is it real? What are we talking about?
When we use the expression global warming, we're referring specifically to the warming of the planet over the last roughly 150 years that has been demonstrably caused by an increase in the concentration of greenhouse gases, most notably carbon dioxide. So it's an anthropogenic effect. It's a signal that rides on top of natural climate change signals, but this is what the phenomenon is. Yeah.
And if I can just emphasize one thing that Kerry just said, which is that we're talking about human-caused warming and human-caused climate change. And people often say, well, the climate has changed before, and so it's happening again. What's the big deal? But it's important to recognize that of the time Earth has been around, there have been no humans for 99.99% of that time. And yes, there have been changes in the climate caused by changes in the amount of sunlight that we get from alterations to Earth's orbit, or changes in the amount of CO2 in the atmosphere because of large volcanic events. Those all happened long before human civilization, long before human agriculture. What we're talking about is a really abrupt perturbation to the stable climate we've had for thousands of years now because of our greenhouse gas emissions, among those primarily carbon dioxide.
The fact that there is a coincidence of this dramatic increase of CO2 in the atmosphere and industrialization, someone may argue is not a strict cause and effect relation, is a coincidence. Do we have other possible explanation? What could reasonably explain what is happening besides an anthropogenic cause?
So, I mean, I would say that it's very easy to show a non-scientific audience a graph which has two curves, temperature and carbon dioxide. You can see that they follow each other. And it would be natural for a smart person to say, okay, well, how do you know what caused that? It's perfectly fine. Well, we know an awful lot more than those two curves. We know physics, and it's very difficult for the two of us to sit up here and give you a course in physics, radiative transfer, convective heat transfer. It is a laborious thing to learn. But this is knowledge that we've had for well over 100 years. The Swedish chemist Svante Arrhenius, a Nobel Prize winning, back in the 19th century, end of the 19th century, when scientists, it was normal for them to dabble in fields outside their ostensible expertise. He did calculations showing that if you doubled the amount of carbon dioxide, he said you'd warm the planet by about 4 degrees C. Even though the knowledge of physics was incomplete, he had no computers, all right? We've known for a long time that if we keep putting greenhouse gas in the atmosphere, it's going to warm. We know for sure that the excess carbon dioxide came from us because of its particular chemical composition. So, yeah, is it 99.5% sure? Yes, it is, I would say. Is there always doubt? In any scientific endeavor, there is doubt. Okay, we can't ever be 100% certain, but it's pretty much a slam dunk that we've warmed the climate at this point.
Right, and you can go look at any of these individual things you might think be causing it, like a change in sunlight reaching the Earth because of the luminosity of the sun, or you could say maybe it's increased volcanic activity, adding CO2 to the atmosphere, and you can look at any of these individually and calculate the numbers and find out, in fact, they don't come close to explaining what's going on. And so for someone to say that the current warming is not caused by our emission of greenhouse gases to the atmosphere, they have two tasks they have to meet to make that claim. One, they have to explain what it is that's causing the warming that by any crunching of the numbers can't do it. And they then have to explain why it is the greenhouse gases we've emitted aren't doing what we know they should be doing from the basic physics and the basic calculations. And those calculations, by the way, aren't just what you might think of as black box climate models run in a supercomputer. A lot of this you can do with pencil and paper to estimate the magnitude, like Svante Arrhenius did back in 1896, whatever year that was. So it's a pretty firm foundation of understanding that we have here.
So the planet was warm in the past. What makes this particular warming that we have alarming or anomalous? It's anthropogenic, but besides that, it's caused by us. Is by any means unusual with respect to what we saw in the past.
People often ask me, well, how do you know that the current climate or the climate we've recently enjoyed is the optimal? And there's a very simple answer to that question. If you look at us as a species, we're well over a few 100,000 years old. But if you look at civilization, depending on who you talk to, it's 6,000, 7,000 years old when we started to settle down, farm, raise livestock, and so forth. It dates back to the end of the last ice age, when sea level finally stabilized. And here's a simple fact. Our civilization is extremely finely adapted to a remarkably stable climate that we've enjoyed for 7,000 years. You go down to the waterfront here in New York, anywhere in the waterfront, and ask, what would happen if the sea level went up 100 feet or down 100 feet? That would be catastrophic. But of course, climate change in the past has done just that. It rose 400 feet, albeit it took 10,000 years for it to do that, the last of the ice age. There's a reason, I think, why civilization didn't develop until the climate stabilized. So the answer to the question is the climate of the last 7,000 years is the climate we're adapted to. Any change, cold or warm, it doesn't really matter, is going to be very disruptive to civilization.
CO2 is the obvious signatures. There are other molecules, or how do you measure global warming beyond CO2? It's just a molecule at the end. And what about the rest?
Well, a lot of it we can do with these calculations. So we can measure, first we can measure these gases in a laboratory and measure their response to different wavelengths of light. And then we can take those responses and put them into a model. Again, not even a big super large climate model, but just a simple model of radiative transfer. So calculating how many of the photons get down through some column of air, up through some column of air, with or without being absorbed by those molecules. So you can use that technique to quantify what the different impacts of these different molecules are. And the reason that Kerry called out CO2 as perhaps being the most important of those molecules is because it is the dominant cause of warming among the greenhouse gases, the most powerful, most in terms of its net effect currently, and it also has a very long lifetime. And that very long lifetime means that centuries from now, even thousands, even many thousands of years from now, the imprint that we will have left on this planet in terms of its climate will be through the CO2 and not through most of those other molecules.
I want to elaborate, if I might, on I think a very important point that David made. Is one of the big misconceptions that I find talking to educated people who aren't climate scientists, even among my scientific colleagues in other disciplines, is that everything we know about climate depends upon some huge black box computer models, okay, called climate models. Well, we have those, and they're useful tools, to be sure, but most of what we know comes from just plain old basic physics, okay? Sometimes embodied in very simple models. I mean, students can be taught, who have a background in radiative transfer physics and so forth, can be taught the elementary aspects of a greenhouse effect in 1 or 2 lectures. It's not difficult for people with the right background. So the physics behind this is solid. Where the uncertainties come in are on the details, which is unfortunately what matter to us. Does it really matter if the planet's going to warm 2 or 3 degrees? You can get that temperature change by moving to southern New Jersey from here or something, right? No, what matters to us is the kinds of things that you've seen here in the United States the last 6 months, horrendous hurricanes and floods, the fires in Los Angeles. The extreme events, right, is what matter to us, and a lot of us in my profession are working very hard on trying to understand how they would respond to climate change.
So I'm getting curious about the models and the things that are not physics, but you have to play with. Can you give us some example? What are the main uncertainties? What keeps you busy trying to fix them? What are you working on?
Well, yeah, go ahead.
Well, one of them is clouds.
Yeah.
I mean, that's what
Clouds.
Kerry was about to say. Clouds are, it's a simple thing. It's a collection of air up there with suspended drops of water or ice in them, so it doesn't seem very complicated. But figuring out the flow of the atmosphere that generates these things in the first place and that allows them to persist for some amount of time is a challenging fluid dynamics problem. And that's where we start to get into some of the details, where a climate model is helpful for trying to tell us what these circulations are and how the clouds might respond. The problem is the climate models can only run on a certain resolution. They can only resolve things that are so big. And that's not because we don't want to resolve things that are finer. It's just that we only have computers that are only so powerful. And so we then have to put in some other models for clouds, which are our best understandings of how they behave, how they respond to their environment. But that then is not rooted in necessarily fundamental physics. We've got to make some educated guesses in there. So that leads to a substantial fraction of the spread and uncertainty. But I want to emphasize that when we say, that uncertainty is already communicated. We'll say, hey, we don't know how much the planet would warm exactly if you double the amount of CO2 in the atmosphere and let the Earth kind of equilibrate. And we'll say, well, it's probably around 3 degrees Celsius, and maybe it's 2, maybe it's 4, maybe it's 5. We're pretty sure it's not 1, it's not 10. I mean, it's in that range. That already encapsulates our uncertainty about clouds and other things. But I would say clouds are among at the very top of that list.
Well, clouds are really interesting phenomena. They work both sides of the radiation street, I like to say. That is, they reflect sunlight, and in that sense, they cool a planet. They also absorb infrared radiation coming up from the surface and from other parts of the atmosphere and re-radiate some of that down. And in that sense, they warm. So getting it right is really difficult. Now, I would hazard that most people in this audience, maybe all of you, have been on a commercial airplane. And if you're anything like me, you look out the window once in a while and you could see the enormous complexity and beauty, I would add, of the cloudscapes. Some of you probably have some really nice photographs of clouds, sunsets, and so forth. Think of how difficult it is to keep track of photons, the thing that carry light, bouncing around amongst all these complicated clouds. That's not easy, and it is therefore the major source of uncertainty.
So when do you run your models? What is your benchmark? How do you compare how accurate it is? Well, but at some point you must say this assumption works better than another one. And something that I think everybody wonders, the planet is big, and you probably have to work with a monster amount of data that coherently must give you a signal over a variety of situations, what I will call noise. Temperature is higher here, is lower there, goes up, goes down, and you have to take these super averages. How does it work? How can you get good data to use against your models? What's the strategy?
Well, I mean, let's just think about the simplest thing. We want to know how much the planet is warmed. And we have a variety of ways to figure that out. The most obvious would be you've got weather stations around the planet, and we've had weather stations around substantial fractions of the planet going back to the 1800s. And those are telling us a story. They're telling us that the planet has warmed up almost everywhere, very isolated spots that have not done so for reasons that we more or less understand. But the planet, if you plot its color with red being warming, blue being cooling, the planet's almost entirely red. And you can say, well, maybe the thermometers have changed and we haven't done a good job of calibrating them. You then want to check, right? So then you can go to a variety of other things. You can look at our satellite data. So satellites orbiting the Earth are looking down and they're measuring the temperatures of different layers of the atmosphere. And they're telling us the same story, the planet's warming. There's another neat technique called borehole paleothermometry, where you can go around to drill holes that have been punctured through the Earth all around, just an opportunistic thing where you go up and, hey, someone's been drilling for gas here, for oil here, for minerals over here, and you lower a thermometer down in it. And what's interesting about that is you can record, in a sense, the older temperature. If I put a skillet on a cooktop, the part underneath the flame will get hot first, and it'll take some while for the temperature to get to the handle. Same thing here, we're warming the Earth at the surface, and that heat takes some time to propagate down into the Earth. So by lowering the thermometer down, we get a record of what that old temperature was. And again, it's telling us the same kind of story, that we've warmed the planet by a certain amount. And then we see that corroborated in a variety of other lines of evidence, from melting tropical glaciers that we know haven't melted in, say, 10,000 years, because we can date the ice to 10,000 years. So it's been sitting there for that long, and it's disappearing now. We have many lines of evidence that the planet is actually warming. And then we can take those data, to get your question in a long-winded way, to the climate models and ask, how well do the climate models replicate that pattern of warming? We can ask the satellites, what's happening to temperature, what's happening to clouds, what is the distribution of clouds, and ask, is this climate model replicating that? And these are all different lines of evidence we use to figure out what models are doing well and should be given the heave-ho, and which should be kept around.
Is it a problem to try to understand a system doing some sort of statistical big average when the system itself is not stable, is changing? What kind of extra complexity you get from chasing a system which is intrinsically, you're saying, unstable? Is this something that complicates your life?
I wouldn't call the system intrinsically unstable. I would say it's been remarkably stable.
Okay.
And in fact, what we're doing is we're hitting the system with a sledgehammer. We spoke about cycles before, and the fact that, yes, it's been warm in the past, but the Earth has tended to drift between cold periods and warm periods on timescales of something like tens of millions of years. And here we are, pushing the system in the direction of a hothouse Earth, if we continue what we're doing, on a timescale of centuries. It's that rapidity of it that is very hard to match from very past analogs. It really is a sledgehammer to the system.
And just to be clear, there is no signature of that rapidity in the historic record.
Well, there are times when things have changed suddenly.
Okay.
When you say historical record, we make a distinction between written human history and ancient history or pre-human. So we call that latter paleoclimate. So the ice cores, the boreholes, and so forth. And I want to just tell this audience how very important that subdiscipline of paleoclimate. It is one of the great success stories of science, full stop, which is largely unsung, which is too bad. Amazing accomplishments to show how the Earth's climate has changed, going back many millions of years. And it's the most amazing detective story in science, involving chemistry and physics and so forth. Well, let me just add to that, there are some really great success stories in understanding that. So as David mentioned, there are these ice cycles. There were 10, what we sometimes call ice ages over the last 3 million years, very nicely recorded in ice cores. Painstaking work to uncover. Same thing going on in Greenland as Antarctica. It was global. We understand pretty well why there were, okay? And that's where the physics come in. In that particular case, those cycles were caused by periodic variations in the way the Earth rotates on its axis and in the orbit of the Earth around the sun. They're called Milankovitch cycles, after a Serbian mathematician who lived in the early 20th century, who said he thought that the cycles, by determining not so much how much radiation the whole world receives, but how much is received up in the high northern latitudes, that were pacing these ice cycles, and modern science has shown that he was pretty much right about that. So there's been remarkable accomplishments about understanding past climate change that gives us some confidence that we understand some aspects of the system pretty well.
Let's talk about the future a little bit. What do you see in our 50, 100 years? What our children are going to experience and what is happening later? Can we do a prediction, a bona fide prediction with the data we have?
With uncertainty, yes. And the problem is, as Niels Bohr once said, prediction's very difficult, especially when it's about the future.
Right.
And it is a tough problem because among many, many other uncertainties, we talked about clouds, a big source of uncertainty in the future is us. We don't know how much greenhouse gas we're going to put up. We can only guess how the world might respond to the observation that we're changing the climate very rapidly by the standards of geological time, very, very rapidly indeed. What will we do? It's a big source of uncertainty. And then when it comes to going in the future, we looked to, among other things, we can run big computer models, we can run simple physics models that all tell us the planet will warm. That much we're confident of. But it's not very useful knowledge, as I mentioned before. We'd like to know how storms change, how wildfires might change. We're also conscious that in the geological past, some of the sudden changes we've seen, we don't really understand very well. And it's clear from even climate models that the Earth may have several different stable climates that are possible under a given greenhouse gas and solar forcing, and you can get knocked from one of these stable states to another. Climate models show that. The paleoclimate shows that, and it makes us a little nervous that we don't understand that. We don't understand, so we can't completely rule out a sudden change, sometimes called a tipping point, going forward, where we transition fairly rapidly to a different climate. Nobody's making a definite prediction that will happen, but we're conscious of our ignorance of how that happened in the past, and it's something to consider when we talk about the risks going forward.
Can I make a prediction about the future?
Absolutely.
I predict it will get hotter. Okay. And I want to let's put some numbers to this uncertainty piece. So I said, we're a little uncertain about how sensitive the planet is to CO2. Maybe it's a factor of 2 uncertainty, from the low end to the high end. But humans really are the big source of uncertainty. We have burned about 500 gigatons of carbon in coal, oil, and gas. We have the ability to burn, is at our disposal to burn, about 5,000 gigatons of carbon. So we have done about 1/10 as much warming as we have the potential to do. And there's a very nice, simplifying, emergent property of the Earth, which is that the temperature you get is about proportional to the total amount of carbon you've burned in the past. And that response is nearly instantaneous. And that means something. It means that if we were to stop burning fossil fuels today, the temperature of the planet would basically more or less hang there, plus or minus a degree. And it hangs there for a very long time. And so we're talking about, and we can get to the very long time piece. What does that actually mean? So my prediction is it's going to get warmer. So this is some foundation for that. We're still burning fossil fuels at roughly 10 gigatons of carbon per year. We've already done 500. So the number's going up, which means the warming we're going to lock the planet into is going to go up as well. And I want to make one more point about that, which is that America's a little bit weird in that we use Fahrenheit. I think it's really unfortunate. The other countries that use Fahrenheit are Belize, the Bahamas, Palau, and the Cayman Islands, I think. So, that's for the Fahrenheit land. But scientists, we speak in the language of, Celsius like every other country. So 1.5 Celsius doesn't sound like very much. But I just want to mention, okay, we've got to convert that to Fahrenheit. That's multiplied times 1.8. And also, that's a global average, including averages over places where people don't live. If you're interested in where people mainly live, say in mid-latitude land, then you got to multiply that by another 1.3. And so when you multiply that through, we're talking about having warmed places where people live by something like 3 to 4 degrees Fahrenheit. And so, extremes are important, but at the same time, it means every single day of our experience on this planet has been altered. Rough rule of thumb, by something like 3 or 4 degrees. And that's a substantial effect when it's applied to every single day and all the consequences that has.
You said the word risk at some point, which I think is a critical term that I'm thinking insurance companies know how to quantify at some point, right? They may decide to increase or even drop your insurance. Do you have a way, is this a term that you use? How do you see risk? How do you calculate the risk in these scenarios? Because it's part of the decision process that our politicians have to take, should be.
So it's a very interesting and important concept, and we use it all the time. There's a formal definition of risk. It's the product of probability and cost, right? So you can have something that's very risky, that's very improbable if it has an extremely high cost. At the other end, you can have frequent small events that might add up to the same amount of money if you measure it that way. There's something very interesting that you find out when you do what I have done, which is to sit on boards of insurance companies, about how that industry works. It turns out, and I think this is an important anthropological point, that over a very long period of time, the events that are most damaging to civilization are events that happen roughly once in 100 years. They're very large, destructive events, but they're frequent enough. If they're less frequent, then even though they're very damaging, they're not frequent enough to add up to a lot. If they're very frequent, we've already adapted to them very well. Like a 20-mile-per-hour wind isn't going to do any damage in New York City. This is an interesting problem because we don't have enough data in the historical record to really get a good grip on what the 100-year event is. We really need 1,000 years of records to do that statistically robustly, right? But they're the most important ones to know, and good luck trying to see if they're changing in time. We don't have the data to do that. So therefore, we're in kind of a tight spot, and we do use physics now. And this is really important because it affects all of you in the audience that have any kind of property insurance policy. I don't mean health insurance, well, that's a problem as well. And that is that the insurance companies have relied on two groups around the world that model, they do catastrophe modeling, it's called, or CAT modeling for short. And they are armies of statisticians poring over historical records. The problem with that, as I've already stated, is we don't have a long enough history to do that robustly statistically. And even if we did, you're getting a realization of climate that was valid about 50 years ago. It's not valid today, okay? This is a huge problem for society. The risk that many, many decisions are based on, including what to charge you for your property insurance, are based on data that is no longer valid because of climate change. That's already happened. And there's a lot less uncertainty about what's already happened. This is being revolutionized because finally the insurance industry and the CAT modeling industry realize they can't do risk that way. They actually have to bring physics into risk assessment. They're doing that. And when they do that, the rates go skyrocketing. And that's a big problem for society. Reactions to that are a little irrational. California just tells insurance companies, you can't charge more than that. Like that solves the problem. They lose a lot of money and they pull out of California. You can't get all-state insurance in California. That's not the way to handle it. What is the right way to handle it, we can have a discussion about. It's a little bit off topic, but you can begin to see the havoc that climate change is already having as insurance companies and cat modelers wake up to the fact that history isn't a good guide to the present.
Yeah, well, I won't go on about the difficulty of trying to get a house insured in California. I could complain about that for you for the remaining time. But I worry about risks to what this planet looks like for future generations. I worry about extinction. We are obviously just warming up the planet. A lot of species will move to locations that are more habitable for them, but many cannot. You've got polar animals like the polar bear getting almost literally pushed off the edges of the earth as we warm up those regions rapidly. We have animals like the snow leopard almost getting pushed up off the tops of mountains as the warming eliminates their habitat. And we have the ocean, which is getting hit by a triple whammy. Temperatures are going up, oxygen is going down, and acidity's going up. These are three things in combination that are going to make it very challenging for the ocean. The oxygen is going down in part because we're warming the water, and warmer water just doesn't hold as much oxygen, but also we're stratifying the ocean and reducing the supply of fresh oxygen down to depth. And the acidity, well, we just burn fossil fuels, put CO2 into the atmosphere, some of that then dissolves into the ocean, and that makes the water acidic. basically, if you've ever had seltzer water, you've had just water with carbon dioxide in it. Or, not literally going to make seltzer water out of the ocean, but we're pushing it in that direction, right? And this is all very damaging for life in the ocean. And we've seen from past events that when we have large burps of CO2 to the atmosphere, we get a major loss of biodiversity in the ocean. One that is one of the worst was about 250 million years ago. It was called literally the Great Dying, where over 2/3 of marine biodiversity was lost. In that case, it was volcanic activity. It was the volcanoes that time, bringing up lava to the surface, covering an area equivalent to Australia, and CO2 bubbles coming up out of the lava. But we're doing something comparable today. It's not lava, but we've burned an amount of coal and oil that would cover Australia in something like 10 centimeters of fossil fuel. There's pure carbon that we've put into the atmosphere. So I worry about risks to other species, and I worry about risks to our own civilization, say from sea level rise, which is, in a sense, a relatively small effect now, but it's a long-term catastrophe. I worry about the health of individual humans and their ability to survive what will be very high temperatures and humidities in locations on Earth, and whether or not people will be able to protect themselves.
I'd just like to add a quick thing to David's lists, and I encourage you to read what our own Defense Department has to say about the risks of climate change from their perspective. And we know from a study of history that past natural climate change in much smaller magnitude has destabilized civilizations, put migration pressures on. We're seeing some of that today, of what migration pressures can do. They're very worried about the potential for climate change to ultimately lead to armed conflict on a global scale. That's them, that isn't me. I'm not in a position to say that. It's sobering to read their own reports, their own feelings about what kind of risks we're taking from that standpoint.
Sort of a dim scenario, right? But we are creative beings. There is always science and innovation and ways to find solutions, I think, right? And certainly there is activities. What do you think is the most promising or the most interesting thing that we can do to at least mitigate, if not solve the problem? What we should do? What can we do?
Do you want to go first?
Sure. Well, I would preface it by saying just a few things of background. One I've already said, and Kerry said it as well. CO2 is the biggest contributor here. And I mentioned before that the temperature that we get for the planet or temperature anomaly is proportional to the amount of CO2 we've emitted. And I alluded to this permanence issue. If we were to stop burning fossil fuel today, the temperature hangs where it is. And the effects of that warming, depending on how much we emit and depending on how you want to measure return to normal, it lasts not for a year, not for 10 years. In fact, it's kind of odd. I've never been asked, how long does it last? I don't know if you've ever been asked that question.
No.
No, it's weird.
Yeah.
I would think if something bad is happening, you might want to know how long it lasts. If I'm planning a camping trip and someone says it's going to rain, I'd want to know, is it for 5 minutes or is it the entire week? But somehow that question doesn't come to mind. But it lasts for thousands of years, if not hundreds of thousands of years, depending on how much we burn. So from that perspective, it's effectively permanent. And what that means, and since there's no easy way to get that CO2 out of the system, it means first and foremost we have to stop burning coal, oil, and gas. It's just physics. It's not any personal desire to not, it's just physics. That's what we have to do. So first and foremost. Now, fortunately, our lifestyle does not depend on burning flammable things as a source of energy. So there are ways to structure our energy systems that don't involve that.
So we have in front of us a risk of climate change, and to really complete the whole philosophy of what you do about it, you have to know about the risks involved in tackling climate change. If it were easy, if there were a simple solution to this, we would have done it by now, right? There'd be no arguments. To switch away from a fossil fuel-based economy is hard and expensive. It's not easy. And we talk about changing lifestyle and all the ethics of the way we live come into that. It's complicated, but here's one fact that you ought to know, is that there are 800 million people on this planet with zero access to electricity, zero, and a lot more with what we would consider substandard access to electricity. They don't want to stay in that situation, and we shouldn't want them to stay there. So it isn't just a matter of, we have to decarbonize, absolutely, but we also have to make it affordable for them to decarbonize, and that's a real trick. The people who study energy say that energy demand will have doubled on the planet by the year 2050. Doubled, okay? So we're talking about rapid growth in demand for energy. For a while, it was thought that that demand had leveled out in the civilized world, but with artificial intelligence and Bitcoin and everything, I'm not so sure. They have big energy demands at the moment that might be solved. So what are the possibilities? And the temptation here, as for many complex problems, is to look for a simple solution, a bullet. But as far as I can tell by looking at the landscape, there isn't a magic bullet. A lot of my colleagues think, well, we just do renewables. That won't work. The renewables are cheap, but energy storage is not. Okay, it's not cheap. It's gotten cheaper. It's not cheap, and most analysts consider it to be way too expensive for us, let alone the third world that wants to grow. So from where I sit, the other piece of problem is the disinformation that the environmental movement has spread about nuclear power. It's one of the most powerful disinformation campaigns I know about, and that might shock you. It's the safest form of power we have ever generated, hands down, until solar and wind, which are comparable. It's much safer than hydro, okay? If we deployed nuclear power at the rate Sweden and France did in the 1970s, they decarbonized all their electricity in 10 years with nuclear and hydro, okay? 50 years ago. So we have the experiment, it's been done, and what's holding us back is an irrational fear, and I really do mean irrational. We can do this. If we do solar, wind, and nuclear, combination will vary depending on where you are. We can do this. But on the one side of the political spectrum, there's a denial, there's a problem, money pouring in from the fossil fuel industry to make sure we don't think there's a problem, and I'm not kidding, it's been documented. It's not a conspiracy theory. And on the left, we have wholesale denial about how to, an important source of solving this problem, and it makes me very frustrated. A pox on both houses, I say.
Thank you.
I'd like to agree with Kerry that we can do this. We need to do two things, and I think Kerry's going to agree with what I'm going to say here, which is that we need to electrify everything. Oh, I got a nod. And we need to decarbonize the grid. And he's nodding in his head. So what does that mean? So electrify everything means we need to consume energy in the form of electricity. And the reason we need to do that is because the things that don't put CO2 into the atmosphere are things that don't make a flammable gas, a flammable rock, or a flammable liquid. They make electricity, be it solar, be it wind, be it hydro, be it nuclear if you want it. They all make electricity. So that means us as consumers, we need to use energy in that form. And then on the other side, the providers of those electricity, the utilities, they need to be decarbonizing, which means they need to take coal and gas off as generators on that grid. So I think we agree there. Where I may disagree with Kerry is the idea that we necessarily need to ramp up nuclear energy. I think for a lot of people, that's a bit of a poison pill, the idea that we'd have to trade one long-term hazard for a long-term hazard of, say, nuclear waste, or the concerns about weapons usable radionuclides or the concern about meltdowns. Now, that doesn't mean that we have everything we need to proceed without nuclear right now. We need storage. So storage is the word that people who work on energy use to refer to things like batteries. And batteries are expensive right now. Lithium-ion batteries are great. They've come down in cost a tremendous amount. It's what allows you to buy an electric car that's comparably priced to an internal combustion engine car. And they're fantastic. They're more fun to drive. They're cheaper to power up. They have fewer maintenance issues. It's all great. But if we're talking about getting, say, where I live, through a week-long storm during the winter, where there's not a whole lot of solar power being generated, we need some backup systems. Fortunately, there are people working on battery technologies that aren't as expensive and don't use expensive things like lithium. An example would be Form Energy, which has its research and development hub just up the street from MIT, where they're developing, or have developed, an iron-air battery. Iron is cheap, air is cheap. And basically they rust the iron to provide electricity, and you charge it up by derusting the iron. And projections are that the cost of that will be much less than lithium-ion batteries, to the point where it's not that expensive to store the energy that you would need, and may not need then nuclear as a backup baseload power source.
Well, David and I will agree to disagree about that. I disagree strongly, but let's not go there. I think the important thing are the things we agree upon. I want to say something about the electrification, okay? Because I think we tend to think of this transition as a pain we have to get through. Well, part of it is. Part of it is going to be really beneficial to us. Consider this. There are 9 million, between 8 and 9 million people on this planet die prematurely every year from the inhalation of particulates that are products of fossil fuel combustion. Folks, that's 3 Chernobyls per day. 3 Chernobyl death tolls per day caused by something unrelated to climate is lung diseases caused by fossil fuel. If we can get rid of fossil fuels, that will be a nice side benefit of that, okay? I happen to drive an electric car, and I won't tell you who made it, okay? And I did that because they're low maintenance. I live pretty far away from a city. It's difficult to maintain my car. I would never go back. And it's not because I have an ideology about electric cars. I don't. They're just much better, right? The engine's really simple, one moving part. Not very, very little to go wrong. No transmission, no oil, nothing. If you ever do this, if you ever drive an electric, you won't go back, particularly when the batteries get a little bit better. There are a lot of nice things that are going to happen, and we should also consider that. And it's not just going to be all pain and grin and bear it.
Let me abuse your expertise. I mean, you are a climate scientist, but this is a very fascinating discussion about technologies. 2 things are missing here. One, there are these stories about CO2 capture, right? There are experiments in Iceland. There are efforts to move away from this stability paradigm. Is it working? And the second is, what do you think about nuclear fusion, which should be the solution? Would you bet on that?
Well, I am empirical, and I don't think we can wait even for better batteries. I think we should go all out with the technology we have and know will work. That's just my position. I tend to be empirical, okay, and not wait for a miracle to happen. The carbon capture is very interesting. And obviously, if we can do it cheaply enough, it's a great thing to do. There's not much downside to burning natural gas, and particularly if you can take the carbon out and bury it. And I visited the operation in Iceland, which is doing it. It's physically, chemically possible to take carbon out of the atmosphere or out of effluents. It's just way too expensive at the moment. But again, it's all hands on deck. People are working at producing better batteries, better nuclear power plants, and taking carbon out of the atmosphere, and we should do all of that. But at the moment, some of those things are too expensive. Yeah.
I don't hold a lot of hope for carbon capture, especially if we're talking about air capture. So this is the idea that, well, we can continue to burn fossil fuels for our benefit, and future generations will just pluck those molecules out of the air and store them underground. To do that would require an enterprise that exceeds the current fossil fuel infrastructure on planet Earth, likely exceeds those costs, but with no direct benefit to the people actually doing it. You have to run this thing out over a century or centuries at extraordinary cost, perhaps in the ballpark of 10 years of global GDP. To me, it's a moral issue. Are we going to not do something to transition away from fossil fuels now and burden future generations with, say, paying a 10% tax on all transactions for a century to build this enormous apparatus to undo what it is we did to them, all the while suffering from the warmer planet we created? That to me is just, personally, I think that's unconscionable for us to be thinking about.
You mentioned fusion, and we forgot to. There is, at least at MIT, and I think elsewhere, for the first time since I've been around, real optimism about fusion. And that's thanks to a breakthrough in magnetic superconducting magnets. It's the bottom line. It's a little bit complicated to explain, but there's genuine optimism. MIT is building a plant outside of Boston. It actually expects commercially to produce fusion power. We're talking 15 years. This is another thing that we can't really afford to wait for that, but we should very much put resources into developing it. Wouldn't you agree? You don't have anything problem with fusion, I take it.
Well, I don't have a problem with doing research.
Yeah.
I love research and I love science.
Yeah.
What worries me is putting our hope in false hopes. Fusion is one of these things that's been 15 years away for the past 50 years.
30 years away. For
there
the
is, well, whatever it is.
It's getting shorter.
Yeah, okay. And so, yeah, we can't wait for that. We can't talk about risk.
Yeah.
A risk of doing nothing in the hopes that there will be some technology like fusion that comes and saves us. And not only does it have to work, but it somehow has to be cheaper than the things that are available today. Yeah. And that seems very unlikely.
Last 30 seconds. What would you tell to a 14-year-old girl here in the room that is looking to her future? What message you will convey about this?
If you're out there, major in physics, major in engineering. Go work on batteries, work on photovoltaics. We need you. Everybody else, we got to electrify. That's the most important thing.
Yeah, I would echo that. And I'd also say that in spite of what you've heard from here and from other scientists and things, there are reasons to be optimistic about this. I mean, we are going to have to change the world, but I think it's going to be a change for the better in the end. And I hope when you're all grown up and our age that things will look much rosier, and I have every faith that that will be the case.
Thank you. Thank you, and let me remind you, as usual, that the New York Encounter requires your support. You are invited to consider donation to the table outside. Use your cell phone and save paper and the planet, but do the donation right now as you go out. Thank you, and to the next one. Bye.